Hello and welcome to our class today on regression. Today's class is going to be a very short introductory level treatment of the topic regression analysis, and the idea here was to kind of position this towards the end of your modules on descriptive and inferential statistics so that you're at a point where you know enough to appreciate how regression uses these concepts. But we will also be revisiting regression down the road, where we will actually talk about the mechanics, about how you implement it, and that is something we will do right after you get an introduction to machine learning and more specifically to supervised learning. Okay, so jumping into what a regression is, essentially a regression analysis, and I say regression analysis here because the word regression itself in different fields is used differently, and in fact even in statistics there's a concept called regression towards the mean, which has a lot to do with regression analysis, but it's also quite different from how we understand how we use regression analysis today. So again, the idea is to use the word regression analysis. So regression analysis essentially is the study of relationships between variables. More specifically, it looks at understanding the relationship between one or more input variables and their relationship to an output variable. And the exact nomenclature is sometimes different. We use the words, I'm using the words input and output. You might also come across the terms response to describe the output, or dependent variable to describe the output. And for the input variable, you might come across the terms explanatory variable or independent variable for the input. Okay, so the idea is to study this relationship between some set of inputs or one input variable to this output variable that you have in mind. And so right from the get-go, at minimum, you're looking at two variables, right? And the whole idea is, have you come across this kind of studying relationships between variables? So what's regression doing newly, right? And the idea is, yes, you've studied, when we started looking, for instance, at two sample t-tests, for instance, right there, for the first time you encountered scenarios where there were two variables involved. To jog your memory, an example of the two sample t-tests that we looked at was, for instance, blood pressure, and the idea of whether the average blood pressure was lower when given calcium supplements versus when given placebos. Placebos are just sugar pills that kind of look like the original medicine. So the idea was there were two variables involved. There was your notion of an output variable or response variable, which was your blood pressure. It's a quantitative variable. And you had another variable. And this other variable was, you can call it calcium. And this other variable, calcium, it's a variable because it can take on two states. It can take on the state yes, meaning you were given the actual calcium supplement, or it can take on the state no, which I'm using as a proxy to mean that you were given instead the placebo. So you had you now have two variables, right? And you can think of your this variable calcium is often called the treatment, but you can think of it as the input variable which takes on two possible states, and you're looking at essentially to see if there is any difference in blood pressure for people who were given calcium versus people who were given placebo. Right there, you're looking at a relationship between two variables. Right? You're looking at the relationship between the variable calcium and the variable blood pressure. Now, another example that we saw in the two sample case was boys and girls in 10th standard in public schools, to see if the average height of boys was equal to the average height of girls. Again, here your output variable is the height, and your input variable is gender, whether you're a boy or a girl. You're looking to see if there is a relationship between gender and height. Yes, the answer is obviously there is, but I mean, in 10th standard is one higher than the other in public schools. Okay, so you went even beyond that, right? For instance, with something like an ANOVA, analysis of variance that we discussed in the last class, you go beyond just having two categories of your input variable. You can have multiple categories. We saw the example where we looked at states as the input variable. You looked at height of 10 standard students, and to make it simple, let's just say boys, but you looked at the heights in Tamil Nadu, Karnataka, Maharashtra. There you're looking at the relationship between state as your input variable and height as the output variable. Is there any relationship? Is there any difference between boys of different states and their heights? And finally, we also looked at something like the test of independence, where you were looking at two categorical variables, and you were looking to see if there was a relationship between them. But so the reason for going into all of this and kind of revising some of the topics is to say that you have studied relationship between variables, but for the first time you're going to go beyond dealing only with categorical variables. Regression analysis is especially powerful because it creates a relationship between two variables, but this relationship both these variables can be continuous and quantitative, and therefore the scope of application for regression really becomes much greater. So to give you an extension, for instance, of some of the previous examples we've looked at, from the top of my head, one thing I can think of is we were looking at the relationship between blood pressure, and you were given calcium pills or placebo pills, right? So there were just two possible states. Now, what would happen if I had 20 different types of pills, which started on one end from the placebo, which had 0 calcium, and went all the way to the other end, which has 100% calcium. And in between the 20 different types of pills, I'm not saying there are 20 pills, there are 20 different types of pills. The different types of pills had varying degrees of varying percentages of calcium, right? So now you have at least 20 states, and those number of states can, especially if you're randomly sampling, that can be infinite number of states, but you just have a range. So it's a continuous quantitative variable between 0 to 100% of calcium, and your output variable still remains your blood pressure. So you can actually create a relationship between these two variables. It can be a mathematical relationship, it can be a graphical relationship, but it goes beyond just 2 states or 3 states or n states. It has the potential to go to infinite number of states of the input variable or variables, and so it can describe richer things. The idea again behind a regression analysis is to not just unlike most of what we've studied with inferential statistics, it's the goal is not just to establish that there is a relationship, but it is to quantify that relationship as well. So a lot of emphasis in a regression is given to the model itself, that mathematical equation that describes this relationship between the input and the output variable, and that can be either linear or non-linear relationship. The relationship between the calcium that is given and the drop in blood pressure, if there is one, can be a linear or non-linear relationship, and you can extend this to all the other examples. Okay, now as with most supervised learning techniques, and that's something that we briefly discussed in the course overview, but it's also something that you will hear a lot more of in the upcoming lectures. The goal of a regression can be twofold. It can be towards prediction, the idea that you now create this linear relationship, and so I can now use it to predict what the drop in blood pressure would be for a given amount of calcium supplement. And that particular amount of calcium supplement might not have even been something that was given in the original data set from which I built the line. But the fact that I used this data to create this relationship in the form of a mathematical equation which represents a line, which represents the relationship between calcium supplements, the amount of calcium given to the drop in blood pressure, allows me, the fact that I've created this allows me to use this tomorrow to predict how much the drop in blood pressure would be if someone came and told me, oh, I'm thinking of giving this amount of calcium supplement. It allows me to make predictions. The other thing that it also does is, given that you're now able to create a mathematical formulation, it gives you an understanding of the world. It gives you an understanding of how much extra calcium that I give, how much of a blood pressure drop will I see. So it's an understanding of how these two variables are actually related, and that's what we essentially call as one prediction, which is one goal, which is to kind of predict, and the other is interpretation, which is to kind of interpret the world that we live in through the lens of this linear relationship. Okay, so let's just talk about, just to give you some feel for where a regression analysis is useful and what kinds of contexts. Here are some examples that we've listed. For instance, so how do salaries of employees get affected with variables such as experience, education, promotions, etc. So the idea here is that salary is the dependent variable, it is the output variable, it is the response variable, and variables such as experience, which might be measured in number of years, education, again measured in terms of number of years after high school or something, and promotions, again a numerical value. How do these variables affect the output variable? Another example is, how does the current price of a stock or a share depend on its past values, and perhaps also on values of the market indices or other stocks, right? A subtle difference here that you might notice, and we'll circle back on this, is in the case of the stock, for instance, you'll notice that the output variable is the price of the stock, but the input variable is also the price of the same stock on previous days, right? So how does the current price depend on its past values? So here the past values become the input variable, and the current value becomes the output variable. We call that time series, and we'll briefly revisit that concept as well. But regressions are also used in that context. Okay. So the next example is, how does sales revenue get affected as a function of advertising expenses and competitors' advertisements? So the more money you throw into advertising, you might have a belief that the sales goes up. But what is that exact relationship? Can I look at past data on different advertisements that have different campaigns, advertising campaigns that I've made for different products, and what my competitors did, and how that affected my sales revenue, and create this relationship? Something else from the mechanical engineering house would be relationship between speed of a car and fuel efficiency within a certain range. When you're driving on a certain gear, what is the relationship between the speed at which you drive and the fuel efficiency? And you could take a sample of 10 cars, make them drive at different speed, or take the same car, make it drive at a certain speed, and get data and try to fit a line in this data to understand the relationship. And finally, another example could be, how does the price of a house get affected by the number of bedrooms, the square footage of the house, its distance from the center of the city, and so on and so forth. Again, some of these input variables need not neatly fit into being continuous quantitative variables, but the idea is that a regression is not constrained by that. A typical application of regression would use continuous variables, but the whole selling point associated with the regression is that it's a technique that's also capable of dealing with continuous quantitative variables, whereas a typical ANOVA or a t-test or any of the tests that we've seen so far are built around the idea of using a categorical input variable, and that's what they're meant to do. Okay, so let's talk about some more concepts associated with the regression. Just for reference, I've shown you a typical graphical representation of a regression, where the x-axis is your explanatory variable, your y-axis is your response or output variable, and each square is a data point. By square I mean each of these small points is a data point, and the idea is loosely, the idea is to kind of fit a line through this data point. And that's what we would call linear regression. If you're trying to fit a line through the data point, we would call it linear regression. The word actually linear regression could also be used when you're doing a linear combination of variables, but some of these variables themselves represent a nonlinear transformation. I think the simple way to put this is, whether you're looking to have a linear relationship between the input and output variables or a nonlinear relationship, you could still use the core concept of regression, but you should be a little careful in terms of what gets called linear and what gets called nonlinear, because often the camp of linear regression could include variables, the input variables themselves, which are nonlinear transformations. And so it would still be called a linear regression, but it won't exactly look like the graph that you're looking at. Okay. You also have the categorization of simple versus multiple regression. The idea behind simple regression just means that there is one input variable, whereas in multiple regression you have more than one input variables. So obviously in the graph that you see in this slide, you're looking at a simple regression because there's one explanatory variable, which is the x-axis. If you have more than one, that becomes hard to represent on a two-dimensional slide. You would have to use a 3D model for two variables, and then after that it becomes much harder. But the idea is that if you have one input variable, it's a simple regression. If you have multiple input variables, more than one input variable, it's multiple regression. We then come to the next concept that we briefly discussed, which is cross-sectional versus time series. The idea behind cross-sectional is that it is not a function of time. Your data is collected across the board, and the time component of it basically means that it's not either a function of time or it's not a function of its previous values. So you can put all the variables in the basket and think that they were all created at the same time, or at least that you don't care whether they were created at different points of time. You're still going to treat them as just different data points and look at a relationship, and that would be cross-sectional. Whereas time series is the idea that previous values in time affect subsequent values. So your modeling techniques themselves become a little different. And a classic example of the time series was the stock example that we spoke in the previous slide, where previous price of the share influences tomorrow's price. Whereas the equivalent of a cross-sectional analysis of that would be to completely ignore the stock price of this, to completely ignore the previous days or previous time period stock price, and just say, can I predict what this stock's value is going to be based on other stocks or other indices? So can I use the Nifty index? Can I use another stock to kind of say, based on these stocks, this is what this stock should be. This is what the output, the response variable stock's value should be. Okay. Next, we just come to the idea that there's this notion of a response variable, or it's called dependent variable, and your input variable is called the explanatory variable or independent. This is terminology that you'll keep hearing, and so it's kind of important. Okay, so the next important point is that we learned about something called scatter plots during the descriptive statistics phase, and a regression analysis in many ways essentially captures mathematically what a scatter plot tries to do graphically. So a scatter plot tries to graphically show you that relationship between two quantitative variables, whereas a regression analysis tries to go beyond that and try to actually fit a line to this, fit a model, to be more general, fit a functional form to this data. And therefore that's the improvement on the scatter plots that a regression analysis does. But often, even before getting into a regression analysis, a scatter plot could be a very useful graphical window into what you should expect, to even see if you should try to fit a linear equation or a non-linear equation, because just visually you might be able to say, this doesn't make sense to fit a linear equation because that's not the correlationship. Another big advantage of scatter plots is that if there are these outliers, and by outliers we mean essentially there are data points which look like they are essentially just errors or something. So let's say you had this data point that was in somewhere completely unrelated, and that could come from an error, and that could completely ruin your regression analysis. But if you see it in a scatter plot, you might choose to say, I want to ignore this data point. That's the idea behind scatter plots and outliers. The next concept is one of unequal variance. We're going to talk about this a little bit, but the idea could be that there could be a very strong linear relationship or a nonlinear relationship, but the variability at different points of x or your input could be different. So you could have something that looked like this in terms of the data. Okay, so this is the line that you're fitting. So there's this so this central line is still the line that you're fitting, and it's a linear line, but the data points in the lower end, so in this side of x, the data points are closer to the line, whereas once you go to this side of x, once you go to the right side of x, your data points are far more spread out, and that influences how the line gets created, and there are certain techniques that are available to kind of counter this problem. It's a problem because, again, visually you might just see this speakerphone kind of shape and say, still I'm just going to fit a line in the center, but this higher variability on one side and lower variability kind of does not always result in the correct line being fit, and you need some kind of a transformation to understand the relationship better. So the last concept associated with this slide and what I wanted to talk to you about is with correlations. So correlations you can think of as a more advanced form of summary or descriptive statistics. We didn't speak about it in detail or in the descriptive statistics part, but the idea is that when you have two variables, just like a scatter plot can be used to graphically describe these two variables, a correlation is a single number that describes that linear relationship, and it's essentially a quantitative indicator of that linear relationship. What you will discover is that in a regression analysis you will also be coming up with certain numbers that quantify this linear relationship, and if you have not already heard of this, you'll come across something called R-square, and that has a direct quantitative mapping to correlation. So it's not a new concept. Essentially R-square is nothing but correlation square, but you will come across it under the term R-square, whereas you might have heard of the word correlation more colloquially used or used more in the context of descriptive statistics. Okay. Now let's just briefly talk about the exact role of descriptive and inferential statistics. Right. So if we start first with descriptive statistics, the whole idea there was either graphically or to quantitatively summarize the data that you see. And one way of summarizing that, one essential summarizing that you do of the data in a regression is to capture a linear relationship which is there in the form of the actual data into a line. And so you essentially summarize this relationship in the form of an equation, and many of you might know that if for a simple line in 2 dimensions you have this formula y is equal to mx plus c. You might have come across that in high school in some form or the other, where c essentially represents the intercept of the line on the y-axis and m represents the slope. So you can think of m as that angle. M represents that slope, and you can in regression often we use the terms beta, and here I'm just using b0 and b1 because I'm representing the sample. Based off of the sample that we have some estimate of b0 and b1, but the idea is that this is some form of summarizing the data, because you are taking the data and you're summarizing it to this single equation. So what is the core concept behind how you do it? And the idea is that it's some form of optimization. It's a form of optimization because you have a set of y's and x's. So you are given a series of y's and x's, and that's your data. And for each y and x, you essentially plot it on this graph, right? You then go ahead and you take a line, and this is that line that we're going to play with, and you choose some criteria to fit the line through the data points. So you might say that, look, my goal is to fit a line through the data points, and I don't want to draw a line out here. That has nothing to do with this data. Right? So what kind of a line has something to do with the data? You might say, well, I want the line to split the number of data points equally above and below it, right? So there's a little bit of overlap there, but you get the point, which is that you might want that line to split the data points. Another idea could be to say, I want the line to go through the two extreme points. So if there are two extreme points, I want the two extreme points to be connected by a line. And you can have various different other criteria. Another very common one could be to say, more advanced one could be to say, I want to minimize the distance between each point to the line. And that incidentally happens to be what we call as the ordinary least squares. But we'll get into that later. But that could be one criteria. Another criteria could very well be that I want to minimize the perpendicular distance of each point to the line. So you could have various criteria, and you can choose some criteria and you can say, I want to achieve that criteria, and that's how I want to fit a line. And so at the root of doing that is the series of techniques on optimization, where you say, I want to do some form of optimization. So you might ask the question, okay, what are you really optimizing? And the answer is, you're really optimizing this objective of minimizing some metric, and let's stick to the metric of minimizing this distance, the sum of this distance. So how are you optimizing that? What can you change? What you can change is this line, right? And what I'm going to do is I'm going to change the two parameters associated with this line, and the two parameters are M and C. Okay, so C is where this line intersects on the y-axis. So I'm going to try and move this line above and below, keeping that slope the same, and try to see where should this line be such that I minimize the sum of these distances, right? Those red lines that you see, my goal is to minimize the sum of these distances, and that's an optimization procedure. That's my objective function. My objective is to minimize the sum of these distances, and I'm going to do that by changing two variables. I'm going to change the variable C, okay, by moving this line above and below, and I'm going to change the variable M by rotating this line, right? So by rotating this line this way and this way. So simultaneously I'm trying to change two variables and thereby find that line. By changing my M and C, I find that line which minimizes this deviation, the deviation of each data point to that line, right? And there are different ways of doing that. I'm just giving you one objective that I might choose to optimize, but at the root of it, you need to realize that ultimately the process of a regression, fitting a regression line, is a process of optimizing, and you might have different criteria. Ordinary least squares, which is one type of regression, uses the criteria of taking this distance of each point to the line and squaring it and trying to minimize the sum of those squares, because each point will have some distance to the line, and then you can take that distance and square it, and then you can go to the next point and do the same, and then you can sum all those squares, and least squares tries to minimize that objective function. But that need not be the only objective function. There can be many other objective functions, but at the root of it, the idea behind putting a line through many data points is to say, I'm interested in maximizing or minimizing some goal associated with the process of fitting the line, and I'm going to do that by changing the two variables that I can, which is M and C, or in other words, your B0 and B1. Okay, So that's essentially the summary statistics, the process of describing the data through a line, and that's how that line gets created. Now, where is the concept of inference, right? The concept of inference again comes from this core idea that ultimately these data points are samples. They don't represent the population. So any B0 and B1 that you calculate are coming from the sample. So they're essentially the sample statistics. But just like X bar in some sense is the sample mean, which is a point estimate of mu, which is the population mean, this B0 and B1 essentially represent a beta naught and a beta 1. So you essentially have the population parameters beta naught and beta 1. Okay, so these are the population parameters. So let's just beta naught and beta 1. Now the idea is that with statistical inference, what you're doing is you're trying to see if either of these terms, beta naught or beta 1, are actually equal to 0. Because if they are, right, then they don't have any business in being a part of this equation, right? This equation that you have out here, now this equation that you have out here, right, that's an equation that you started with before you even fit anything. Now you're just in the process of finding out your B0 and B1 through some optimization procedure. Now imagine a situation where X has nothing to do with Y, right? X has nothing to do with Y. Now you calculate a sample of X's and a sample of Y's. If you had an infinite number of samples, you might arrive at the conclusion that B1 is truly equal to 0, and therefore this term itself becomes 0 and should not be there in this equation. But you still only have a sample, and that sample is 5 data points, 10 data points, 20 data points. So it's perfectly possible that even though true beta 1 is equal to 0, that's the null hypothesis, even if that is true, it's possible that you just take a sample of y comma x's and you get some beta b1 which is not equal to 0. So b1 winds up not being equal to 0 even though beta 1 is equal to 0, right? So you might be erroneously thinking that x has this relationship to y, whereas in reality beta 1 is 0. Okay, so the whole idea is to do a statistical test to test the hypothesis that beta 1 is 0. So the null hypothesis would be that beta naught is 0, and you can think of it as also beta 1 is 0, and it turns out that under certain assumptions of normality, and even when those assumptions are violated, to some extent central limit theorem kicks in, it turns out that the distribution of the betas of these coefficients winds up being t distributed, so like a t distribution, and so you can use essentially a t-test to test the hypothesis that each of these coefficients are actually equal to 0 or not. And the idea is that if you wind up you need to reject the null hypothesis and reject the hypothesis that beta 1 is equal to 0, and only then can you actually have that term in the model. And this becomes really useful when you have multiple input variables. So you might have something that says beta naught plus beta 1 x1 plus beta 2 x2 and so on, and it can go on, right? You can have many variables. So which of these terms actually get to stay in the model and which don't is not just a function of this magnitude of beta 1 and beta 2, because that's the magnitude becomes really a function of it becomes also a function of the magnitudes of x1, x2 and the units and so on. But what really determines whether these things stay in the equation or not is the inferential statistic test that you do for each of their population parameters, which is for beta 1, for beta 2 and so on. And insofar as you can reject the null hypothesis that these are equal to 0, then you can leave them in the model. But if you cannot, if you cannot reject the null hypothesis, then these terms don't have any business being in the model. Okay, so that's the idea behind doing statistical inference on the individual parameters. You will also notice that in a typical regression analysis or a regression analysis output, independent of the software that you use, you will find an inference for the overall model. So aside from the inference that you see for beta 1, beta 2 separately, for a given model, you will have an inference, and that inference again uses the concept of an ANOVA. And the way it does that is by looking at, if you remember the ANOVA in the past, you had the concept of mean squares between and mean squares error, where the mean square between was trying to quantify the effect of each treatment or each state of the input variable, and mean square error was trying to quantify the inherent noise that was there even within each state. Here, however, you don't have a finite number of mean square betweens, because there could be infinite states of the input variable x, right? So you have a single term that tries to capture how much of the variability is being captured by this linear or non-linear model that you built. How much of variation in x, okay, is being captured by this equation. How much of the variation in y is being captured by this model versus how much of the variation in the data points is not captured by the model. So one becomes the mean square of the model essentially, and the other becomes the mean square error, which is just which is some notion of general noise that is there in the system. And essentially the ANOVA out here again we will be using the f-test the same way as we used the f-test when we were describing the ANOVA in the previous class for categorical variables, and thereby rejecting that null hypothesis would mean that this model explains variability in y, whereas if you fail to reject it, the idea is that you cannot say that this model essentially you cannot say that this model is any different than if you were to just randomly choose y's completely unaware of what the model was. So no variability in y is being explained by different points in x. So and essentially when you think of it, that's nothing but the concept of a straight line. It's essentially a concept of something where you're not describing the variability in y at different points of x. So at various points of x, you're looking at the same position, same position of y. Okay. I hope that gave you an introduction to the concept of regression. And like I mentioned, after we introduce the idea of machine learning and supervised learning, we will be revisiting regression to look at a more in-depth treatment of how you actually do it, and give you an understanding for how the core derivations are made. Thank you.